Hi everyone. We, the team 6 members, selected the material graphite. Coming to its atomic structure. Graphite's atomic structure features layers of carbon atoms arranged in a hexagonal honeycomb lattice, with each carbon atom forming 3 covalent bonds with its neighbors, resulting in a delocalized electron system that allows for electrical conductivity. Its electronic configuration is 1s2, 2s2, 2p2.
The reason Team 6 has selected graphite as a material under consideration for the material science activity is that graphite is a very useful material and is used in variety of industries and industrial products. One such industrial product is a lithium-ion battery. The lithium-ion battery uses graphite as a negative electrode, and hence, based on its properties, we have selected the graphite material. The graphite electrode in a lithium-ion battery is also coated with a layer of zinc oxide to enhance its properties and to show better performance.
Okay, now coming to the crystal structure. So this figure shows a crystal structure of graphite, a common allotrope of carbon, and graphite has layered structure made of two dimensional sheets of carbon atoms arranged in hexagonal pattern. So here you can see each carbon atom is sp2 hybridized and forms 3 sigma bonds with other carbon atoms in the same plane, creating hexagonal trees, as you can see from here. And also the layers are stacked in AB pattern, and you can see here the black solid surface labeled as alpha atoms, which have direct neighbors above and below in adjacent trees. And also here you can see the white open circles or beta atoms have no direct neighbors in the adjacent trees, contributing to the weak van der Waals forces between layers. And now coming to the zinc plane structure, this diagram shows zinc plane crystal structure which forms a cubic structure commonly seen in compounds like zinc sulfide or all. So in this structure, the atoms are arranged in FCC cubic lattice, and here you can see the black spheres represent zinc atoms while the blue spheres representing sulfur atoms. Next we are coming to the synthesis procedure of graphite. The first step is mix carbon-rich materials like electronic coke with the binder like coal tar pitch. And the second step is shape the mixture into desired forms such as rods. And the third step is heat the shaped materials to about 1000 degrees Celsius in an inert gas like nitrogen to remove impurities and all. And the fourth step is we are here using heat the carbonized material again to 2500 to 3500 degrees Celsius in an inert gas to turn it to an graphite. And the fifth step is let it cool slowly in an inert atmosphere. And the last step is purify or machine the graphite depending on how it will be used.
Now moving over to phase diagrams. Phase diagrams are very important when it comes to material science, as they are used for predicting the structural stability and various properties of the material, hence will ultimately guide in choosing the right material for the right job. Coming over to the phase diagram of graphite. At low pressures, graphite is stable from the diagram you can see, but at higher pressure it transforms into cubic diamond or hexagonal diamond. Depending on the temperature, at even higher pressures and temperatures, carbon melts into a liquid. This helps in understanding and controlling the temperatures and pressure necessary for the preparation of the graphite electrode, as well as designing of the graphite electrode. The phase diagram after this is of zinc oxide, which exists in two phases, woodsite at low pressure and rock salt at high pressures. The solid curve marks the phase boundary, where the transition pressure peaks around 1200 Kelvin and 5.5 gigapascals, indicating a temperature-dependent first-order phase change.
The property table of graphite. As you can see, we listed out mechanical, electrical, electromagnetical and optical. In mechanical, density, hardness, Young modulus, tensile strength, compressive strength, shear strength, Poisson's ratio, friction coefficients. The values of these are given here. And also for electrical, we have listed electrical conductivity, electrical resistivity, temperature coefficient of resistance, and it is in the range of 10 power 4 and here 10 power minus 5 to 10 power minus 6 ohm meter. And also coming to electromagnetic, we are having magnetic accessibility, relative permeability and absorption of EM waves. And also here coming to the optical, we included refractive index, transparency, reflectivity and absorption coefficient. Here you can see it is in the range of 2.7 and opaque in bulk, transparent in layers, high for infrared and visible lights, high for UV light. Thank you.
Graphite morphology as revealed by scanning electron microscopy (SEM) and transmission electron microscopy (TEM shows a layered structure with stacked sheet of carbon atoms and can be further characterized into various forms like flakes, plates or particles. SEM is used to visualize the surface morphology of materials including graphite, and its advantages include provides information about the surface features such as cracks, folds and agglomeration of particles, and it can be used to analyze the morphology of graphite powder and other graphite based materials. TEM, which is transmission electron microscopy. Internal structure imaging. TEM allows for visualization of internal structure of materials by transmitting electrons through a thin sample, and its advantages include it provides high resolution images enabling the observation of nanoscale features, and it can be used to study the layering structure of graphite. It can be used to study the morphology of graphene, which is derived from graphite.
So let's move on to the nanomaterial synthesis or the nanomaterial details regarding the graphite electrode or the graphite material considered in this activity. Zinc oxide is often deposited on the graphite electrode as a thin layer in the form of zinc oxide nanomaterials. This can be done by a process called atomic layer deposition, which can be classified as a bottom-up approach of nanomaterial synthesis. In this process, the graphite is first cleaned with solvents and optionally treated with O2 plasma for better adhesion. Atomic layer deposition is done at low temperatures with the range of 100 to 150 degrees Celsius to protect the substrate using alternating diethyl zinc and deionized water pulses separated by nitrogen purges. Each cycle deposits about 1.5 angstrom of zinc oxide, allowing precise control over film thickness, resulting in a uniform, well-adhered coating, ideal for energy and sensing application, or in this case, for the graphite electrode, enhancing its properties.
Manufacturing process. The manufacturing process of graphite typically involves several key steps, especially when producing synthetic graphite, commonly used in electrodes, batteries, etc. Here are the main steps. So first step is raw material selection. Petroleum coke and coal tar pitch binders are the primary raw materials. Coming to the next step, which is grinding and sizing. We reduce the particle size for uniformity. So next is mixing and slurry preparation. So here graphite is mixed with binder and solvent and additives are added. Next is coating. Coating on copper foil for uniform layer formation. So next one is drying. So drying is done to remove solvent and improve adhesion. Next is calendering or rolling, which is used to control thickness, improve conductivity. Next one is cutting and punching, which shapes the electrode sheet. And next one is electrode dyeing, drying and vacuum treatment, which removes residual moisture. And the next step is assembly into cells, in which it combines with cathode separator and electrolyte. And the last step is formation and testing, in which initial charge discharge cycle and performance check is done.
So let us see how knowing material science has helped us and what we infer from this activity. Knowing material science has helped us in understanding the atomic structure of the graphite electrode or the graphite material that is considered for this activity. It has helped us understand the structure-property relationship and the phase diagram utilization for designing a material that is suited for its application. We have also seen the optimization of properties for the graphite electrode application, as well as the synthesis and manufacturing advancements done for this material. What we infer from material science. Material science plays a crucial role in chemical engineering by enabling design and selection of materials that can withstand harsh environments, high temperatures, and mechanical stresses. It helps us understand how material structure affects different properties and different applications. By combining the knowledge of materials with process engineering, chemical engineers can develop more efficient, durable, and sustainable systems for different fields and industries.